was always really nice to him.
Yeah, and crack. So one of it equals to KD. Let's just imagine this equals to KD. Then from this we can say
I want to be this person for you.
this,
So
can we imagine just L and everything is KD, 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 then they even happen, of course. But if one thing, this is bigger, this is smaller, this is KD, then what? Then KD equals to...
Okay, so we have a couple things we got to get through today, so we should get moving. One is I want to show you how to simulate data, which means to draw the theoretical curve that you'd expect from a certain binding model. And so it's not exact. Actually, the Prism is quite powerful. It can actually even put in simulate noise and stuff. So you can sort of simulate data. We're just going to do it more primitively and just draw the curve, which is useful to do. And this is useful to do in general. I think it's shown one of the examples on one of the old exams. One of the Prism problems on one of the old exams starts by doing a simulation of the data and then analyzing it. And so I just want to teach you how to do that, primarily for that reason, although it is useful in general. Then the second thing we need to talk about logarithmic binding plots. And the reason this is important, this was going to be a little segment of a lecture, but we ran out of time, so I'm going to cover it today, like what these are and how they work. And then we want to talk about going from total to free ligand. We talked about that in theory yesterday, but the reason we need to do it in practice is because to actually make a scattered or a hill plot, right, those are in free ligands. And those are other reasons you might want to go to free ligand, but those have to be in free ligands, so that's something to do. And then
and just one compound. It means
we have time
one
for
of
the
these.
second data set, the file I
Not
sent
this one.
yesterday,
So
is
this one.
physical
Because
stoichiometry
yeah, it's just equals.
analysis, and that's just a good example. So this is a lot to get through in an hour and a half, but I think we can do it if we keep on track. Okay, so if you go to,
No, of course, experiment.
it's not, yeah, it's no, you need to go to displays. Right. Yeah, no, it's fine. It's just, I don't know why it does this. I guess in some, yeah, exactly. And go to arrangement. It defaults, yeah, mirror displays. It defaults to somehow having, I guess it's if you're giving a lecture and you want to read your notes on the screen and have something on your screen and something else on the main screen, it defaults to having the screen being different from the projected screen. But yeah, if you mirror displays, it's good on that. Okay, in your resolution, I think this should be good. I think it should be good. That was mirrored yesterday. Let's see if you can run Prism. If you can run Prism, it's good enough. I think so. So, yeah, I think hang on a second. They changed this just a little bit. I mean, here are some sample data that might be useful for you to take a look at. Although again, the way that some of the curve fitting things in models are described is variable. Some of them are good, some of them are not so good. But anyway, I think probably let's start with a single y value and just say okay.
Yeah, I can't see okay. Hold on. You have to change the...
Oh, then you are going to change the resolution. If you can't see it on your monitor, you've got to change the resolution. Yeah, that's better. Yeah, actually, before you do that, there is something. We try scale for a moment. No, I don't like this. You see, get out of this if you can.
No, that's not going to make sense for us to read.
Yeah, maybe.
No, cool. I'm sorry.
Can't you just cancel?
Sorry, this is a new operating system for
Yeah,
me.
it's okay.
Yeah.
Hey, I guess hit best for retina display. I don't know.
that's what we were on.
Yeah.
I mean, this is classic.
External displays? External display?
That was the one.
That's-
That was
that's-
the one where I
Yeah,
was
hit that. I think see if it does something different this time, which it should not. Since it's a computer, you would hope it would behave the same way. So yeah, but hang on one second. Let's now go back to arrangement for a moment.
Drag the
Yeah.
screen.
So basically, So do you see the screen, the little blue box?
Yeah, no, that's okay. The problem is the resolution. Go back to display. I mean, it used to allow you to actually specify the resolution, and then it actually looks much better. And this is typical the way that Apple is going, in my experience. Everything's got to work exactly like it does on an iPhone and be as stupid as possible. I think your only option is desktop for Retina display, right? You got to be able to set the screen resolution in order to independently set the resolution for the projected output. But it used to do that. But entropy. It is leading us into a state of chaos, aided by Apple computer.
People that are out there.
Okay, yeah, we're gonna have to live with this, I'm afraid. Yeah, so let's go for one. Yeah, exactly. Enter one x value, and now I think if you hit analyze here, so now you have a data graph. You have analyze, and scroll down here a bit further. Simulate data. Simulate column data. Yeah, hit OK. And number of data sets. Let's go for 4 data sets. And population column means. I think that what that will do is, actually, if you have multiple y values for every x value, it will actually give a random distribution of them according to some Gaussian function. So I think that will simulate noise in the data, but let's not worry about that. Number of rows. So yeah, they changed this totally since the last version. Okay, so number of rows. I think if we simulate the data with 100 points, that should be in. Actually, let's put in 1,000. It's a computer to deal with. And just put 1,000 down with all of the number of rows.
Go down. Simulate data. Column data.
Column mean.
Then 4.
Can you click column mean? No, actually, the word. Hit hook. See what that gives us. Curious. Okay. Hit that random variation. No, I'm sorry. Yeah, that one. Sure, that one too. Yeah. Yeah, this is adding noise to the data, which is what I expected to do. That looks reasonable. Actually, better cancel this entirely for the moment. I used to just go back to analyze. Of course, what we want to do is we want to use a function to generate curve. It used to be called simulate data. They've changed the name to generate curve. Okay, better.
Simulate data journey.
Plot a function. Exactly what we want to do. Okay, good. Which used to be called simulate data, but now the simulate data has become something mysterious. Okay. And so now it'll let us use any of the equations that it has or that we have input, right, which is sort of useful. And so, for instance, we can go to the cooperative binding equation of free ligand concentration. And why don't we take a look at that just for a minute? You go up to the little star thing over on the right. Yep. Up. Yeah, if you go up to the right, that little sort of. No, the one next to it. Yeah, over to further. I don't know, snowflake. What is that? What is that shape? Snowflake? It's a cog. A cog. Cog. Okay. Yeah. Oh yeah, actually it is a cog. Okay, good. Okay, so this is B max times delta plus x to the n, kd to the n over x to the n. Okay, so this is our standard equation in free ligand to describe any kind of binding equilibrium, irrespective of its degree of property. So this is good. We have it yesterday. And so then you can say, I think you can just say okay or cancel. Doesn't matter. You haven't done anything. Okay, and so now what we want to do, that's good, plot a family of curves. Let's do that. And let's plot a family of 4 curves. Actually, let's plot a family of 6 curves. And so x values, let's go from 0 to, why don't we go to 200. And we can say this is micromolar. What the hell? It's hard to make up. And now if you hit options, let's see what's there. Plot the first derivative, plot the second derivative, plot the integral. This, you can decide how finely sampled the line is. Column labels, label each column with a parameter value. Why don't we label each with a parameter value? And now we can select it. Let's make the parameter value, we label it with n. And now go to parameter values. And now we have 6 of these, right? And so now we can, actually, if you can select all, and then let's start down here. So let's for Bmax, let's make this 10. And delta, let's make it 100. This is sort of arbitrary. And n, let's just start with it at 1. In KD, let's start with it at 20. Okay. And now let's go and individually modify these. Let's go, so unselect all. Maybe if you hit select all again, we'll unselect all. Now, well, I just click curve A. Okay, and so we like, so curve A, this is an n equals 1 curve, fine, and we'll use 20, so that's fine. Let's go to curve B, and let's keep it at 20, but let's make this instead, let's keep the same parameters, but let's make the KD 50. We're on curve B, we're making the KD there 50. So let's go to C. The what? That's okay, we're going to change it. We'll check everything at the end, yeah. He is right about that. If you just click C.
I just unclick all the rest.
Oh yeah, unclick all the rest of them. Yeah.
So we want it to be on B.
So what was A?
Yeah, what was A?
A was where we started.
Yeah. KD is 50?
Yeah, and then, yeah, exactly. In B we're changing the KD to 50.
Okay.
And then go to C, yeah, unclick B, go to C, and now let's make cooperativity 2. And then we can leave that one at 50, it's fine. And then let's go to D. And now make the cooperativity here 20. I'm sorry, make the KD 20, sorry. Yes, verbal typo. And now let's go to E.
You should have already been 20.
Well, she had modified it by accident.
Oh, okay.
You should be okay with that. And then n here, let's make n here 3. I think 50 is fine for here for now, and then let's go to the last one and make it 3 and 20. 3 and 20. Now, what am I doing here? I'm exploring how this binding function behaves with different KD values and cooperativity values, right? So just to understand how this influences what the data looks like, assuming we have a plot of relevant and free ligand concentration.
What's curve D? Sorry, I missed it. Can we click through all of them?
And how is F different from N?
That's curve D.
Start over.
A grid of n equals 1, 2, 3, right? And KD
is 350, 350.
KD is equal to 20 or 50. This is what we're setting up.
D is not different than A.
So we have 1, n1 with 20 and 50, n of 2 with 20 and 50, n of 3 with 20 and 50.
D and A are the
Right? Because I just want to see, I want to get some model data, I want to see how it behaves when I change the dissociation. I mean, you're going to know some of this, but I want to get it to show you can actually do it more quantitatively. Right? So we're getting 6 conditions that basically fill in the grid. So we have N1 with KD 2050, N2 with KD 2050, N3 with KD 2050. Is that easier to follow?
That's not actually what we did.
Yeah.
Do you want to go through
So one.
D needs to be,
Yeah, that's okay.
250.
Yeah, I think you have it right. So why don't you hit OK, and let's see what we get out of that. And that might actually help everyone. Yeah, just hit OK. Okay, so you've gotten a bunch of data plots, right? In the end. Yeah, I mean, if you go back to the graph, it sends you there, go to the graph. Yeah, sorry, data table. Sorry, go to the go to the data table. Oh, I don't know. Oh, it's changed this too. So it graphs data one. I don't know why. No, that's bizarre.
Plot a function, results.
Your plot function.
Yeah, results plot a function. Thank you. Yeah. Again, this is totally different. It used to just make a data table out of it. Go figure. Okay, but so it is now basically calculated the values of those functions, right? Over the range we told it to. And so this is simulated data. This is simulated data without noise. You could go in and add noise to it now, and so it's quite powerful in a way, but we're not going to. So that could be quite useful, right? Suppose you have some data and it's so, there's noise and you can't figure out whether it's cooperative or not. You can simulate some data and put in noise and see at what point things just become difficult, right? So there's some useful things about it. But we're doing something just a little bit simpler today. I'm just showing you can simulate the data trend, and then we can look at how it behaves, and you can qualitatively understand things about it, and semi-quantitatively understand things about it. So it is now plotted equation. It is plotted curves matching those equations. It is generated data for curves matching those equations, and it's plotted them. So if you come down to plot a function. Okay, so let's color code this in a way. First of all, let's make it bigger. Just grab the corner, grab it down, pull it all the way down here. Cool. And just a little bit. Let's keep it on the screen. That would look good. Yeah, just up a touch. If you do that, when it gets this is just like Word or Excel. When you get the straight line cursor, it's going to change size, and when you get the crosshair, it's going to move it. So if you go to the middle of it, just go to the middle of it. It's the crosshair on the. Let's see what happens there. I hope I'm not too surprised by its behavior. Yeah. Okay. Good. That's good. Oh, yep. Good enough. Yep. Stop. And now go over here, and you should get the line cursor. Click. Yeah. Click it. And now, yeah, it's a line that goes way high. Go very high. We can make it this big, right? I don't know why it defaults to being so small. It doesn't make sense to me. But okay. Now go over here and click it. Yeah, good. And what if we wanted to simulate further out? Well, I told it to plot up to 200, and then it said it has 150 line segments enough, and so I can tell it to plot to 300 or whatever. But I think it's good, right? So let's color code these to make it a little bit easier to see. So if you click one of the lines.
So it's supposed to be shown.
And now let's change this so just instead of easy. So instead of thickness of 2, let's go to thickness of 4. And for let's make the n equals 1. We can keep them black. That's fine. And so now you can go up to say plot a function. Oh, n equals 3. We're at the wrong. Yeah, let's start with n equals 1. And so let's make the thickness 4. Let's make it colored gray instead of black. Yeah. Yeah, that's fine. Good. Just say okay. I'm sorry. Just come back over here. Yeah, that's good. I guess you have to close it. Upper left. There's the. Okay. And now, okay. So I think this is good. So let's go to n equals 1. The second n equals 1.
So this was second.
All right. Well, that's fine. Yeah. So go to the first. That's fine too. And just make it 4. And that's good too. Okay, now go to n equals 2. And let's make it 4 and make the color blue. A deep blue. I'm sorry. Sorry, I can't see one too exactly. Yeah, so go to color. Yeah, so the reason this is because you got to bring this. This is like a mathematical thing about color coding. If it's black, you have no color, so you got to bring it out of black before it'll let you put in a color. Okay, there you go. That's good. That's cool. Yeah, and then that deep blue I think is good. It's like that. That's good. And now I think actually you can just drag this in. Yeah, that's fine. Okay, now let's go to n equals 2, the second one.
Did you change it?
So we just have. That's what they were talking about. That I have 3 and
Oh,
equals
no.
1.
So this is
All right, well, we're going to fix that in a minute. Let's just, for now, you can do it here. If you go to 4, yeah, go to color, that's fine. And go bring it up again to the midway.
n equals 1.
Bring it up actually
1, 2,
lighter.
3, 3.
And now select a light kind of blue.
This is KD equals 20. This KD equals 50.
Yeah, that's good.
KD equals
That's good.
20.
Yep, and then thickness 4. And now go to n equals 3, and let's make this red. And why did I choose blue and red? Yeah, that's good. Perfect. And then go to 4. Why did I choose blue and red instead of red and green? Because 50% of males are red-green colorblind, and if you plot things in red and green, 20% of the male population will not be able to see the difference. So I had a meeting once. I got completely waylaid when I was a junior graduate student. I went to a meeting and there was a very famous old professor. He got up at the end of my talk and he understood nothing about it. And it's because I had different things I was comparing in red and green, and like I couldn't figure out what it was embarrassing because he was like a famous person, and so at midnight I realized that he was red-green colorblind and he couldn't see the difference between the rest. Okay. Yes. So yeah, go to the next one. And yeah, and we just let's actually go lighter. Let's make it a lighter red. Yeah, let's look at there and then bring the scroll bar up a bit. Yeah, even good. It's good. Yep, and then that's all good. Yep, and now you have to go back. So you can sit okay. And now you have to go to right, it's just 2 the reciprocal place. Now you go to plot a function, results. You go to change parameters, right? Go to the red graph with the blue arrow. Change parameters, and now you just go to the one that was messed up. Yeah, unclick the other one exactly, and that should be n equals 2. Yeah, and now everything should be good. You go back and. So what we've done here, I have similar colors for the graphs with the same cooperativity, right? Gray and black. Actually, let's double click the gray. Let's switch the gray to black. So
what did we change?
Make this one black. Yeah, exactly. Just take it all the way down. Good. And then go to the other one, and go to the other n equals 1 and make that one gray. And I'll show you why. Then we'll come back to the graph in a minute. Hit the color. And get in the middle of it. Yep, good. Good, and now say okay, and go back to graph. Okay, so the lighter colors are the n equals, the lighter colors are the KD20, and the darker colors are the KD50. And the black and gray are n equals 1. The blue and cyan are n equals 2. And the red and orange are n equals 3, right? So this is useful, right? Because we can now see qualitatively, we can see semi-quantitative. We can get an idea of, in a semi-quantitative way, what the influence is on the shape of the curve from changing these parameters, right? So of course, this is an LF. Why don't we put that down here for now? That's LF. LF. Yeah, that's fine. Yeah, you can do that. That's good. And this isn't fractional saturation because it's actually put in here signal. And actually select the whole graph, just anywhere, right? Yeah, click. Yeah, I think that will work. You go up there to no, it won't work. Select the frame like on this side. Now select the corner down here. Let's see what we get out of that. Click. Yeah, click. Click just nowhere. See what happens then. That's not working. Yeah, cancel. I can tell you, no one has ever handed me a graph with the labels on it being large enough. No junior scientist has ever handed me a graph with the labels on it being large enough. And I mean, most reviewers are like elderly people like me who don't see so well anymore. But it's also true, when they reduce it for printing in the journal, right, you'll make it nice and big. They reduce it for printing in the journal, and of course you can still see the data in the labels, even for younger people, shrink to unreadable size. So these, and this is, I guess some same pathology here. These, we want to make the, it doesn't matter today so much, but the labels should be way bigger. You can do it there, but we can do it. So just select over here. So the question is doing it step by step. Actually, double click.
If you click on the
Titles and fonts, yes, thank you. Exactly. You can change all of them, and yeah, you can hit that font. And go up to like 24.
Yeah.
If you click on the little thing,
Yes. Okay. That's good.
There's a
Here?
underneath the sheet, like,
Oh, you just drag it.
Yeah, well, okay.
why?
Yeah, at that point.
Well,
Okay, you
I
know,
don't
cancel
know.
here. What, if we have to do
you're-
separate yeah, what, now that thing up at the top,
Yeah,
right?
yeah.
With the A, you see the big A?
Yeah.
Hit that like 5 times.
Okay.
Yeah, and then click down here and hit the big A 5 times as well.
Here?
Yeah, just the axis. The axis goes.
Be fine.
there.
And now you can just drag it. Yeah, click. Yeah, no, that. Yeah, exactly. Well, yeah, exactly. You have to play individually. It's fine. And then down here.
Just went to him.
This is the last time we're gonna do this.
Right there?
Okay, now grab it in the corner and just move over. So it's fine. It's good. That's good. Now grab it down here in the corner, and then you can just drag once you click the line. Yeah, click the line. Well, then see, try to get that cursor with the, and just drag it over so it's the whole thing's going. If you click it in the corner, in the intersection point of the axis, click there. And, let's not worry about this. It's good enough. Okay. Now, so this is, so what do we see, right? Well, where's the KD in this graph? Where are the KDs here? Yesterday we had a graph in total ligand and our, but this is a graph in free ligand. Where are the KDs? In 50%, if it's free ligand, which in this case it is, because we made the whole thing up and we're saying it's free ligand. If it's free ligand, half saturation is KD. So KD is 20, KD is 50. Does that make sense?
Yep.
Yeah, that's what I put with the equations that we encoded in there, right? And so that now, so I now have an example of 2 different KDs and then different n values. So what happens when the n value is different? Well, so the black or gray ones are n equals 1, and they're hyperbolic and they saturate very slowly. As you go from n to 2 and then to n to 3, it becomes more sigmoidal, right? So you have more curvature down here, but it also saturates more rapidly. And that makes sense, right? Because if we look at y bar equals LF to the n over KU to the n plus LF to the n, right? If we go to 2 times KD and it's not cooperative, we would have KD over 3 KD. It's only 2/3 saturated at 2 KD. If we go to n equals 3, we would have, at 2 KD, we would have 8 KD over 9 KD, and it's 90% saturated, right? So that polynomial behavior makes it saturate much more rapidly. And now by looking at it graphically, you can see that in, I think, a more intuitive and conceptual way, right? So higher KD, once you get to free ligand, right, higher midpoint, more higher cooperativity, more sigmoidicity, sharp, whatever, more curvature, sharper sigmoidicity, and importantly, faster saturation. And this is quite important because with real data, like if you look at n equals 2, it's not that curved, right? It's a little bit curved. And you could do this, and it's sort of interesting to do, but we don't have time to do it. Now, if we put noise in this, it would rapidly become very difficult to see that curvature. And that's actually why the scattered plot is useful in a way. It lets you see it more sensibly. But actually, the main thing the scattered plot will look at is, right, when n equals 2, there's more curvature here, but that's, you know, it's low numbers, it's going to be noisy. It saturates significantly more rapidly. And then the scattered plot, basically by looking at the ratio, you know, by looking at the chord to this point, right, is going to be able to see a big difference between them. The scattered plot is a way to really sort of visualize more directly the rapidity of the saturation and the curvature. So now we could go to a scattered plot, and Prism makes this very easy to do. But please note that we simulated data in free ligand, right? If this were in total ligand, of course the scattered plot, you know, can also be done, but you have to go to free ligand first. Prism assumes that you are knowledgeable enough to only convert to a scattered plot automatically if you have put in free ligand. And so if you have a graph in free ligand, it will do all the math necessary to make this a scattered plot. But it's assuming you're not going to be foolish enough to try to do this in graph in total ligand. So you better, okay, so we can do that. And I think Now, how do you do this in the new version of the program? Let's see what happens when we hit analyze. Let's go up to transform. Yeah, go scroll up, scroll up, scroll up. Yeah, that's good. And see what other thing, the function list, see what else it was willing to do there. Under transform, you have pharmacology and biochemistry transforms. Does that sound promising? The scattered plot and the hill plot are transformations, the data, right? They're taking the numbers you have and putting them in a different format. So let's try pharmacology and biochemistry functions. Heedy, Hoofsty, Haynes, Wolf, Hill, Lineweaver, Burke, log, scattered. And it even knows that we wanted a scattered plot this morning. So that's good. And for other things, it's going to ask you for additional parameters. But in this case, it's scattered plot is willing to do without any further advice. So let's see what happens when you do a scattered plot. Hit OK. It has behaved in a curious manner in that it has only given us one data set, but at least it's telling us which data set it is. It's the n equals 1 y data set. Hey, can you scroll down and see if it has anything? Yeah, it's okay. It's actually just done them. Yeah. And why did it have to do this?
Because you only have one line.
Well, because the x-axis in the scattered plot is bound receptor. And so for each one of those things, at a given data point, at a given x value, right? Let's go back to the graph for a minute and understand this. Yeah, I'm sorry, it's a plot function. Okay, for a given x value, there's a different bound receptor in each one of these things, right? So for a common x value on this graph, it's going to be a different x value on the scattered plot. And because Prism Prism insists on just one x value per row, it has now put all of these things into separate blocks. But there's a useful thing when you go back to that scattered plot of function. So here it has 10, and here it has. Yeah, I guess that. Oh, I know what it's doing. Okay, it's fine. So here it has 10. Go up to the top. It has 10 again. And so this is a trick. Although you can only have one x value per line, you can have the same x value multiple times in the same data sheet. So if you want to do a plot with multiple, if you want to plot multiple curves on the same graph, you can actually put one of them here, and then just go down below it and put and then put the next one below it. It doesn't require an x value on every line, and it doesn't even require the x values to be ordered, right? So this is again, this is the psychology of the program. In some ways, it's not very interesting, but it is useful. So the point is, if you have your x, y data up here, right? And now you want to plot some data that has different x values. It'll only allow you to have one x value per line, right? But what you can do is then you can take the next two columns and you can have totally different x values down here. And it will then plot them in the same, it'll use the, and so, right, so in this case, the x values are always in the same place. So then you'll have a second set of x values down here that go with these, right? So x1, y1, x2, y2. It'll only allow one x value per line, but you can have multiple blocks with different x values in different segments of the table. And so you can, in that way, plot multiple graphs with different x values using the same data graph. But you need to do it this peculiar way. It doesn't care if you have the same x value multiple times. It doesn't care if they're numerically ordered, right? So that's a trick to put multiple graphs, to use a single data table to get multiple graphs. You can also, within the plotting window, you can go back and you can add plots to a graph from different data tables. Maybe we'll do that later. But so anyway, so now let's see what it did. So plot a function. Why don't you come down here and change this to scattered? Just double click it. So does this look like what you expect? Should the scattered plot look this way? For n equals 1, it would be a straight line, you know. So something has gone wrong, and this is again, this is a booby trap. For the scattered plot, to do this transform automatically, it's assuming you're showing fractional saturation against free ligand. So if you have total ligand or you have a signal, it will do something stupid. You know, and so this is typical of computers, right? They'll do what you tell them to do. But especially when the instructions are not very clear, you may end up telling them to do something stupid, and you have to be careful about it. So let's go back and sort this out. So let's go back to, actually let's delete, well, let's leave it there as it might. So let's go back to plot a function, to the results. And now let's go, go analyze, and let's transform it again. Actually, let's see fraction of total. Does that look interesting?
Sorry, that was because the scale wasn't from 0 to 1?
Yeah.
Okay.
Yeah, exactly. Yeah, actually, this doesn't look right. They rearranged everything here, but we'll find it cancel. Go back, analyze again. Let's go to transforms. No, let's go to normalize. Let's see what is there normalize? Search. Let's see what that does. How is 0 defined? Smallest value in each data set. How is 100% defined? Last value in each data is largest value in each data set. Well, why is that? Is that going to be good? So smallest value in each data set is fine. I mean, even with real data, that would probably be a reasonable guess. It's where 0 is, right? Is the largest value in the data set a good choice for the maximum value? So what this is doing, this is going to take your data point, right? It's going to take a y value, and it's going to subtract out some baseline value, and then it's going to normalize it by taking basically max. Let's do it this way. So it takes y value minus some mid value over the max value minus the mid value, right? And what we want to do is capture, we want to go to fractional saturation, right? We want to go from signal as a function of LF to fractional saturation, right? And so what it's trying to do is basically normalize everything between these two limits. So picking the minimum value of the data as the minimum point is reasonable, but the maximum value, right, if it hasn't gone to saturation, that would be dangerous, and that's going to be rather inaccurate. In this case, because it's simulated data, we know the maximum value should be 110. So we're going to put in 110. If it weren't simulated data, you would be well, and I've picked it the same for all of the graphs, which simplifies it. In a real case, you would be well served to do some kind of preliminary curve fitting and use that to estimate where it saturates. But for the moment, the advantage of the simulated data is we can just say 100% is y equals 110. We have y equals 110. So we do, because we've set that. And plot results as fractions. And let's create a new graph of results just so we can sanity check it. Okay, so hit OK. And so now it says the normalize of plot in there. And what do we get? Well, this looks, it's a bit of, you know, they're all black and it's ugly, but it does tell us it's done the right thing. Okay? Yeah?
So why?
Why 110?
Because the range is from 0 to 1.
Oh, because the equation that I simulated, when I simulated the equation that I simulated was the following: was signal equals 10 plus 100 times y bar. That's what I simulated, right? So the maximum value of the simulated data is 110 because that's what I plugged in.
So this
110 plus 100, right? Y bar goes to 1 at the max. 10 plus 100 is 110. Okay, good. Okay, so now let's try to scatter. Let's go back to now. Let's go to the normalize and let's see if the scattered plot works on this. Now, whatever happens now, I promise you that last year, if you did the similar things in the earlier version of the program, this did work properly. So I'm a bit curious to see what's actually going to happen next. But we'll be optimistic until we have a reason to be pessimistic. And now we will go back and analyze it again and go to transform. And, okay, yeah, and then select biochemistry and pharmacology functions, and select scattered, and again, there's no, and we want a new graph, say okay. And so let's see if this looks better. Ah! This doesn't look so bad, does it? This one actually looks decent. So two of them, are they exact?
How did you get that? How did you get that?
So, is this
So
sort of what
do you have the
said?
normalized one?
Yeah.
Yeah, go to the normalized data.
Sure.
And then you analyze and do the scatter, transform.
Okay, so the ones that are straight lines are the n equals 1. The non-cooperative ones are straight lines. And I think you can see that even the n equals 2, right? The n equals 2 looked curved as hell, right? And so this is actually quite a powerful way to see whether it's cooperative or not, right? It's transforming the data to make it to really look at the shape. Okay, and so you can see, first of all, the pitfalls in making a scatter plot, it has to be in free ligand, right, or it's not going to work. And it has to be, well, it's using fractional saturation. You could also calculate that offline, right? But for it to do its transformation, and then it's taken, once you've given it fractional saturation versus free ligand, it has calculated bound receptor over free ligand, and then plotted bound receptor over free ligand compared to bound receptor. And of course, the bound receptor is proportional to fractional saturation, so it's actually plotting, right? What it's actually plotting is fractional saturation divided by free ligand as a function of fractional saturation. And it works, right? And I think this also illustrates how, even in n equals 2, the scatter plot becomes dramatically nonlinear, and so it is quite useful to see whether there's maybe cooperativity or data. And remember, most cooperative enzymes, cooperative enzymes typically have a cooperativity of 1.5. They don't really have a cooperativity typically of all the way to 2.
Yeah.
Some can be more cooperative, like hemoglobin or ProELS. But typically it's 1.5, and so at that point the shape difference is even a bit more subtle. But I think you can see that the scatter plot is changes shape so dramatically with cooperativity that you can really. This is quite a useful thing if you do it properly and carefully. Okay, so the next thing, let's do a Hill analysis. Let's go back again to let's go to the well, actually let's do the same. Let's go to plot a function and results, and let's transform again. In this, you do another biochemical and pharmacological transform. No, analyze the data again, creating that's good. We want a new analysis, and now go again to pharmacology and biochemistry. Let's go to Hill. Now, additional parameters: y Vmax or Ymax. Why does it need to know that for the Hill plot? What is the Hill plot? The Hill plot is the logarithm of basically bound receptor over free receptor. How is it getting this value? Well, what it's doing, effectively, in the Y bar space, in the signal space, right? What it's doing is finding the baseline and it's finding the max. And then it's going to take this ratio as, right? The log of bound over free receptor is the log of this quantity divided by that quantity. So to figure this out from the data, it needs to know where, right? It needs to know where saturation is. It needs to know, it's the same issue with the scatter plot. For the scatter plot to calculate bound receptor, it needs to know where saturation is. I'm sorry, when we did the transformation of the data to fractional saturation, it needed to know where saturation was. We needed to tell it that. Same thing here. It needs to know where saturation is. If it knows where saturation is, it's just going to do a simple arithmetic calculation. It's going to take this distance, the distance between this data point and this bottom baseline as being proportional to the amount of bound receptor. It's going to take this distance as proportional to the amount of free. It's just going to do that those simple subtractions and take the ratio of them, and it will use that as the fractional saturation. And so it needs to know the maximum value for that reason. And again, that's one reason why it's useful. To keep this going efficiently, I mean, we could get to it anyway, but to keep it going efficiently this morning, it was useful to use the simulated data because we know what the proper value is there. So Ymax should be On this scale, it's 110, right? Because the data that we input was 10 plus 110 times y bar is 110 is the next one. And wait, x values, did we enter log of concentration or concentration? We entered concentration, right? Okay, so say okay, and let's see if this works. And now, why is it, let's go back to this just 1 second.
Because it was asking what we entered it as.
Hang on 1 second. Can we actually, yeah, let's go back here 1 second. Yeah, I actually think that this is also, I think in the end, slightly wrong because of the same, okay, but it's a good place for us to play around with it. Why in the hill plot was it able now to put these all in the same line? What is the hill plot? The hill plot is log of this ratio versus log of LF. So if all the data points have the same, if all the curves have the same LF values as what's true for the data that we simulated, right? It can take the log of LF, and all of them will have the same x value, right? The x-axis in this case is a direct, simple function of the variable, right? And so therefore, all the curves that have the same x values have the same log LF values. You can put them all in the same line. Right. And so that's why. Okay, so let's see what it plotted. Does this look right? Is the hill plot supposed to be curved like that?
N equals 1 should be a straight line.
Yeah, well, they should be a straight line. The slope should be the cooperativity. So you're seeing some evidence of that, right? There's differences in the slopes. And if you looked at it carefully, the steeper ones would be the more cooperative ones. So it's doing something, but there's something, it shouldn't be curved like that. Now, real data will look curved like that when you do this because of the complexities, actually knowing exactly where the saturation point is. But they should be that curved. Something's gone wrong here. What do you think that is? It has once again assumed that you have already transformed the data to fractional saturation, right? So because we haven't transformed the fractional saturation, right? It is assuming, it's assuming that this is going from 0 to 1. So once again, you have to normalize the data to get the proper hill plot. So let's go back and do that.
Can we use the one we normalized before?
Sorry. Yes, you can use the same. It's the same data. It's the same normalization. You go back to the normalize of the plot, and now again go to analyze, and transform, and transform. Yeah, no, let's do a new one. And biochemistry and pharmacology, Hill, and what's Ymax now? Well, it's already normalized, so Ymax now is 1.0. Right? You know, the stupid thing is, it's clearly, it is taking a Ymax value, so it's willing to do part of the normalization. It's really just dumb that it won't also take the Ymin and do it itself. But that's, you know, it's a trap, and you just, as long as you're aware of it, you understand. So now I think this will work. And of course, the same concentration. Okay. Okay. Now, is that better?
Yeah.
That's better. It looks like now. What is it actually plotted? When I did the hill plot, I told you it was going to look something like.
Was it 1.0?
I told you the hill plot was going to look something like this.
Oh, you did a hill plot of the scatter plot.
What did it do?
Oh. Yeah.
Rather than plotting logarithm of bound over
Yeah,
free,
that's
it's
what it
plotting
says.
logarithm of free over bound. And so it's just inverted the y-axis by changing that ratio.
Yeah,
But it's not, everyone see that's not a big deal.
Like going in one.
Right, it's still true, right? The slope now is now positive instead of negative, but starper slope, higher cooperativity. And you know, I think you can see that, actually, why don't you just make one of them, just hit the n equals 1, come down, yeah, come down over here. Actually, hit just any one of these graphs. Just hit one of the points. Just double click one of the points, right? And now up there go hill plot of that, and go to n equal 1. And now make it. Let's make this one red.
It's the first.
Yeah, sure. Oh, no, symbols. Show the symbols, sorry. Their color. Yeah, under the symbols. Then just make it red. Just, that's good. Make it a bit brighter if you go up. Up. Yeah. Okay, just, it's fine. Hit OK. Okay. Okay, so the least, right, the one with the lowest slope is the n equals 1, and then the more cooperative one's the ones with the higher slope. And if you find the other one, right, there's another one down here with a different, with the same slope, but that has a different crossing point, right, because the KD is different. So this is not a great way to see the KD, because, right, the logarithm, right, basically what you're looking at. In this graph, you're looking at log LF, right? It's plotted, I believe it's actually plotted log base 10 of LF. When you look at log base 10 of LF, right, the twofold difference in KD is significant, right? A twofold difference in log KD is going to be a really small number, and that's why these are all the intersection on this axis is the KD, right? In a plot relative to LF, the half saturation point, which is where the bound and the free are equal, right? When bound and free are equal, log is 0. So when log is 0, that's the 50% saturation point. In LF, that should be the KD. So 3 of these crossed are used crossing the same KD, and the other 3 crossing another KD. But in the logarithmic coordinate system, right, a twofold difference in KD or 2.5-fold difference in KD is just like log 2.5 is some small number. So it's not a great way to see differences in KD. But it reveals the cooperativity, right? And the good thing about this is that, you know, you can actually, from the slope, you get the cooperativity. From the scatter plot, if it's higher order cooperative, if it's cooperative from the scatter plot, you cannot, from the scatter plot, figure out how cooperative it is. This has the advantage of letting you figure out how cooperative it is. But the scatter plot is a very sensitive way to tell whether there's any cooperativity at all. In particular, with cooperativity of 1.2 or 1.4, which is common for, that's actually probably the most common value that you'll get if you do this kind of stuff a lot. The scatter plot's going to be a very good way to say yes, it's cooperative and stuff. Okay. So we've actually skipped around a bit. We've done this in a way. We haven't yet done from total to free equal ligand, and I do want to do a practical example of doing that if we do very little else. But we have to now talk about the logarithmic binding plot. And this is important. This again, I wanted to cover in lecture and did not, so this is essential content now. So let's go now to let's go back to our graph. Now, the question at the moment is what's going to happen, and this is important, and we'll take some time to explain, about 10 minutes to explain this in detail. What will happen if I make this axis logarithmic? Why would I want to do that?
Maybe if you want to see the saturation?
Exactly. So just to see this, let's go back to the data for this. Let's go back to the plot of function result. And let's change the parameters. Let's change, hit that little red graph, and let's change the parameters. Yeah. Yeah. No, I think the one on top. Hit that. And so now let's change the parameters of something. So rather than let's go to B. Let me click A. Go to B. And instead of 50, let's now go. Let's go to 250. And now go to D and also set that to 250. Instead of 200, you just put 5 between it. Yeah. I'm sorry, hang on, leave that, sorry, no, go set that back to 20 because these are just flipped, it's fine. And then for C, I'm sorry, go to 250. Yeah, go to 250, just put a 2 right in front of it, it's 250. And then go to, unclick that and go to F. And go again to 250. And now let's go to options. And let's make this 1,000. And then go to function. And now I want to, if the KD is 250, I better go beyond K50 to go to saturation. So let's make this 1,000 too. Okay. Okay, so so now let's go back to plot of function in the graph. And So something went, oh, that's still 50, we changed that one. Let's go back to, let's consider, this is really confusing for everything. So yeah, change. No. Change, yeah, no, that's weird. Yeah, go ahead, sure, change. Yeah, I'm sorry, yes, try those. And then one of the n equals 1 is wrong. Go to B. No, I'm sorry, go to E. Yeah, that should be 20. Because you're just inverted order or something. So say okay. And now go back to the function. And now there, okay. Now, so we have a KD of 20 and a KD of 250. If you're dealing with different isotypes of a receptor in pharmacology, or you're dealing with a mutant you've made, is it possible you'll have two variants of a receptor that differ, where one has a binding constant of 20, a KD of 20 nanomolar, and one has a KD of 250 nanomolar? Yes, the other data that I was considering bringing yesterday instead of the data I actually brought was a case where we've done exactly that. We've made a mutation that changes the KD of something by about 15-fold. So it's pretty normal to have affinity differences of this kind that you want to analyze simultaneously. And in drug discovery, right, in hormone, in age-old pharmacology, looking at hormone interactions with cells and stuff like that, different hormones like estrogen versus progesterone versus testosterone, looking at how they stimulate some response, you will have large differences in the affinity and the efficacy. When you're doing that in drug development, as you're improving a compound to make a better drug, you'll have very large differences in the affinity of compounds. It's nice to be able to compare them all at once. Can we really see what's going on in both of these curves? No, this is just so compressed down. And suppose you had things that differed by affinity in a matter of a factor of 100. Well, then it would be even a bigger disaster, right? This would just be a straight line by the origin by the time we had a plot that was big enough to see something different in a factor. Right, a factor of 100 from a KD of 20 would be KD of 2,000, right? So just getting all the data on the graph is highly problematic. Now, does the logarithm, if we make this axis a log axis, does that offer us something good? How does a logarithmic function behave? So I'm going to say x prime is equal to logarithm base 10 of x. And how does that behave, right?
No. You have to change it in the theta.
So when x is equal to 1, what is the logarithm of x? What's the logarithm of 1? 0. 10 to the 0 is equal to 1. All right, so this is like this. When x is equal to 10, what's the logarithm of base 10 of x? 4. When x is equal to 0, what's the logarithm of x? Minus infinity, right? Right? The logarithm, right? With 0, you have to, so 10 to the minus infinity is approximately equal to 0, right? If you want to see this in a different way, if x is 0.1, right? Suppose x is 0.1, what's the logarithm of base 10 of x? Negative 1. 10 to the minus 1 is 0.1. So at 0.1, this is going to be negative 1. So what does this function do? What this function does is it compresses the axis above 1. And it expands the axis below 1. So as we go from 1, and but logarithms are really looking at multiplicative increments, and so the fact that I'm doing this at 1 is sort of incidental. It's going to be the same principle, basically, no matter what the units are where we do this. Of course, in logarithmic coordinates, 0 is a problem. It's negative infinity, but anything non-zero is fine, right? And so what this just does, it compresses the axis values above a certain value, and it expands the values below a certain value. So if I convert this to a logarithm, it's now going to compress this axis. It's going to move these things together in some region and move them further apart in another region. So let's go ahead and do that. And does this, however, can can I now put data with much different KD values on the same graph? Yes, I can, because logarithm of 10 will be 1, logarithm of 100 will be 2, logarithm of 1,000 will be 3, and logarithm of 10,000 will be 4. So this will enable me to put things with radically different KD values on the same graph and see them. Okay, so that I think is clear cut. We're going to do in a moment. How are these things going to behave? How is the shape of these things going to behave when I do this logarithmic transformation? How will the shapes of these curves change when I do the logarithmic transformation? Well, in some region, it's going to compress down the data, right? So this curve, for instance, is going to get compressed inward. In another region, it's going to spread out the data. So something down here is going to get spread outward. So this hyperbolic function, right? So let's consider the hyperbolic one, non-cooperative hyperbolic function. When I do a logarithmic transformation of this black curve, it's going to compress it in here, so it's going to get steeper in here, but it's going to spread it out down here. And so it's going to get actually, right? It's going to compress here, spread out here. What's going to happen to it? It's what?
More like a straight line.
It's going to become sigmoidal. The hyperbolic non-cooperative curve becomes sigmoidal when you do the logarithmic transformation. And so this is an important point qualitatively. You look for sigmoidicity in a linear axis, that means cooperativity. In a logarithmic axis, everything is sigmoidal, and you can't be confused by that, right? So this is important because many people will open up a journal any week, and you're going to find someone plotting data, especially in drug discovery, pharmacology. You're going to find people, and in developmental biology often too. You're going to find people plotting data on the logarithmic scale, and you've got to understand qualitatively what that means. The sigmoidicity in the linear scale means cooperativity. The sigmoidicity on the logarithmic scale means nothing. Because even the hyperbolic function, when you do this logarithmic transformation, this part of the curve gets compressed, this part of the curve gets spread out, that induces a sigmoidal shape in even the hyperbolic plot. Okay, so Prism will do this for us if you double-click this axis. Now, how are the different levels of cooperativity going to behave? Okay, so everything's going to be sigmoidal. How is the graph going to vary with different levels of sigmoidicity here? So hold on one second. Now what's going to happen when I do this, I'm going to compress data in one region. But they're all going to be compressed, right? This is a monotonic function. Does anyone know what that means, monotonic? Monotonic means an increase in x produces an increase in y. It's not linear. The same increase in x will produce a different increase in y, but it is monotonic. Increasing x always produces increasing y. Right? So when we do this transformation, something that is lower in x is going to be compressed less. Another way to think of it, something that's further out in x is going to be compressed, right? If I'm looking at this point compared to this point, I'm going to do this transformation. It reduces the difference in the value between these points, in the increment between these points, but it is still an increase. Right? This is a monotonic function. Greater in x is always greater in log x, and vice versa. So that means that these curves cannot cross when I do this transformation. Right? Because the function is monotonic, they will not cross. Although I'm going to make them steeper and more sigmoidal, they cannot cross. So the steeper ones here have to continue to be steeper in when I do the transformation. So the steepness will still be an indication of related in some way to the cooperativity. Steeper graph, more cooperativity, but all of them are sigmoidal. Even non-cooperative is sigmoidal. Cooperative is more sigmoidal in a sense. Okay, so we understand that. Now let's do it. And we could of course we could take the data in by hand or in Excel or wherever and take the log, but this actually will do it automatically. So if you double click the axis and scale in the upper right, it says linear. Linear. Log base 10.
Yeah, well, it's almost
Okay.
okay.
And so now, so don't be confused by this. So this is one log unit. This is 1, 2, 3, 4, 5 in log, right? After you take log base 10, this is 1, 2, 3, 4, 5. But it has, instead of calling this 2, it's called it 10. Well, because LF is 10. So it has properly functionally compress the axis, but it's still labeling it with the actual LF. So this is sort of useful in a way, though, because you can see, right, it is true. LF is 10, LF is 100, LF is 1,000. In logarithmic coordinates, this is, of course, 1, 2, 3, 4. It's spread out that way, 1, 2, 3, 4. But it has labeled it according to the starting parameter. And so that is actually useful, but it can be confusing if you haven't thought about it. Right? And the logarithm of 5 is, I'm sorry, the logarithm of 3 is roughly 0.5, right? 3.3 something is, sorry, the square root of 10 is roughly 3.3 something, and so half of this should be, right? So this works, if you think about it, but let's not get caught up in that. Okay, so now we see that this has worked, right? We have very different KDs, and if the KD were 1,000, what would have happened? Well, if the KD were 1,000, I would now get my midpoint in LF over here, and they would still all be on the same graph. And so this is quite useful to do. But do you notice anything else about, okay, so this I hope all makes sense in a qualitative way, and most importantly, when you open a journal article, you've got to look carefully about what the axis is, right? And notice, this doesn't say log LF. So you have to look at how these numbers are spread out on the axis to see that it's a logarithmic data finding plot. And so if you look at this quickly and you say, oh, it's LF, this is sigmoidal, it's cooperative. Is that right? No, it's not cooperative because it's really, although they're labeling these in linear space, they're plotting them in log space. It's a log plot. Even a non-cooperative finding is sigmoidal in a log plot. And again, this is commonly done this way in many research studies, so it's really important to know qualitatively what's going on. Okay. But the greater degree of sigmoidicity, when it is cooperative, you get greater sigmoidicity, right? It's steeper. Okay. Now, is there anything else you noticed about this?
Harder to see the saturation.
It's a bit harder, but I'd say it's easier. It's easier to see that it's not saturated. Okay, so it's right. You're not seeing right, but it's easy, right? You can see, right? You see that it's not saturated, but it's different depiction of that. What else do you notice?
They're all sigmoidal.
Do the shapes? How do the shapes of these things compare, in particular between the two groups? The ones with the same cooperativity have identical shape, right? The shape is still diagnostic of the cooperativity. The shape of this graph and the slope of it in the middle is still indicative of the cooperativity, and so that's been preserved, right? For a given degree of cooperativity, you get a given shape. A higher degree of cooperativity, you get a steeper shape, but a given degree of cooperativity, you get a given shape. Higher, steeper, but fixed shape for a given cooperativity. Now, why is that true? Why is that true?
It's for the same reason as it was.
So n is exponent, so n is increasing.
That's sort of it. So let me explain this relatively quickly. Take about 5 minutes to explain to you why this is true. All right, so if we start with a graph like this, with y bar versus LF, and I'm just going to plot two curves and say they have the same degree of cooperativity, whatever it is. And I'm going to have them now with two KDs, but I'm going to say these have the same degree of cooperativity. Okay. So now I'm going to transform this plot. Instead of y bar versus LF, I'm going to transform this to y bar versus alpha. And I'm going to define alpha is equal to the logarithm of LF. I'm sorry. I've gotten one step ahead of myself. Sorry about that. Alpha is going to be y bar divided by KD. And so, of course, for the different curves that have different KDs, I will be transforming it differently. Right? And so this is KD1, because this is an LF plot at 50% saturation. At 50% saturation, this is the KD. Right? So in this case, I have KD1 and I have KD2. I have different KD values for different graphs, but I can transform each graph individually. And I will do that. And now, what is this going to look like? What will happen when I do this? Well, the equation here is y bar is equal to LF to the n over KD to the n plus LF to the n. Now, what I'm going to do is I'm going to multiply through the right. This is just our standard equation. What I'm going to do now is multiply the top and the bottom by 1 over KD to the n, right? I'm going to just multiply now the top and the bottom by 1 over KD to the n. What do I get when I